rockets. You know them, you love them, they're the big sticks we send into space. But the majority of the size you see on a rocket and the majority of its weight is actually just fuel. See, for a rocket engine, you need a fuel and an oxidizer. They mix in this combustion chamber and shoot out all the hot exhaust. That's what gives us thrust. But how efficient is that? The answer? Not very. See, for our chemical rockets, we get a specific impulse at its highest of about 400 seconds. Now, what specific impulse, you ask? Specific impulse, the force the rocket provides divided by the mass flow rate times the gravitational constant. Now, this is the force of the entire engine divided by its mass of expended fuel. This is a direct measure of efficiency. So, with a chemical rocket burning liquid hydrogen and liquid oxygen, the best we get is 400 seconds of specific impulse. Now, usually that number is a whole lot lower. See, first stage boosters and even second stage, they need more thrust rather than focusing on efficiency. So they usually burn kerosene and liquid oxygen, and their ISPs are somewhere in the 300s usually. But if you want to go far in the vacuum of space, already in orbit, thrust isn't as important as it is on the ground. Well, you maximize your fuel efficiency, and you'll have more thrust per every fuel mass, meaning for the same fuel mass, you will get greater overall impulse. Meaning for the same weight in fuel, you can go a heck of a lot further. But how do we maximize our specific impulse? See, our force for our engine is the mass flow rate. Can't maximize that. That's our denominator here. That'll hurt us. Our exit velocity, the velocity of the gases coming out of the engine. That we'll come back to. The change in pressure between the inside of the engine and the outside, and the area of the exhaust, so the area of the bottom of the nozzle. Now, these two are tied together, and there are expansion ratios which are just optimal, so you can't play around with those too much. Which brings us back to our velocity of our exhaust. Now, burning liquid hydrogen and liquid oxygen, you can only get so much thermal energy from that combustion. So, let's say you really need to maximize your specific impulse, but still have enough thrust to where you can go somewhere quickly, unlike ionic propulsion. Enter nuclear thermal propulsion. Basically, you use the thermal energy of a nuclear reactor instead of combustion. You take your liquid hydrogen, you pass it through the reactor, and you let it go on out the back, all heated as exhaust. Liquid hydrogen is a cryogenic fluid, and one of the coldest ones we have at that. If you're in a room negative 200 degrees Celsius, it'll try and boil. That's how cold that is, for reference. So, you pass it through a nuclear reactor, it's going to absorb all the heat that it physically can from that reactor. So let's say you have, I don't know, 1 megawatt reactor. Besides some minimal losses, you're getting 1 megawatt dumped into your fuel. That heats it up a heck of a lot. And so, when it leaves the engine, it is so hot, and in the vacuum of space, it comes screaming out of there faster than anything we can achieve with a combustion reaction. So, where does this theory actually get us? I mean, sure, you can theorize all day about, this engine, how it would work, but we've put it into practice decades ago through the NASA NERVA project. And the only reason that was canceled and not followed up on was just because of the budget. NASA is currently contracting Lockheed Martin to make a new nuclear thermal engine for use by manned spacecraft in the future. See, let's say we have a certain amount of fuel for a chemical engine and a certain amount of fuel for a nuclear thermal engine. Because of that increased thermal load being dumped into your fuel, and because it's leaving at such high velocities, raising our specific impulse, we can achieve roughly twice what we can with our most advanced chemical propulsion engines. So, in an ideal world, pound for pound, your delta V should be roughly doubled. Now, delta V, that's your potential change in velocity based on how much fuel you have and your engine's efficiency. Basically, if you have 100 meters per second of delta V, you have a potential change of 100 meters per second to your velocity. So, where does that get us? Times 2. Where does that get us? Let's say you're trying to get a manned spacecraft to Mars. You want to get there faster because humans don't like being in space all that much. So, you have twice the delta V, you spend it, you still spend the same mass of fuel, but you get there twice as quickly. That is the benefit that we are currently working to exploit from a simple thermodynamic equation.